All right, so in example 2, find the limit as x approaches 1. We're going to use the table of values here. We can even use the same table of values as we did in the previous one. What happens as x gets close to 1 from the right? What happens as x gets close to 1 from the left? Let's just do 3 points. 0.9, 0.99, 0.999. Oops, I put these guys in the wrong spot. So this is less than 1 and this is greater than 1. Okay, for greater than 1, we'll say 1.1, 1.01, 1.001. Again, I'm going to use my nifty-galifty calculator. Top in brackets, x squared minus 1 divided by x minus 1. I go to my table of values and, oh, look at that. It saved my x values from the previous example, so I can just see right there, it's 1.9s and 2.1s. So this is, oops, sorry, the smaller ones were 1.9, 1.99, 1.999. This was 2.1, 2.01, 2.001. Okay, so the green represents f of x, and the black represents my x values. This is a t-chart technically, right? So as x approaches 1, we can see there's an agreement from both sides. The function approaches 2, and therefore the limit exists. Okay, I want you to go back to your graphing calculator. I want you to graph it. Ooh, never mind. Our plots are still on. Yes, great question. Super awesome to do this on a French calculator. Oh my goodness. We need to turn off the stat plots. We're going to go second Y, enter, and we're going to hover over the off button. There we go. Now I can go to graph. And my window is not correct, so I'm going to fix my window because this was still based on the previous example from yesterday. Okay, so let's go back to -10, +10, -10, +10. Graph. So there's my function. This is a really grainy image of my function. But essentially, it looks like this. I want you to take a closer look. What happens when x is actually 1? We know we have a point of discontinuity. Is it going to be a hole or an asymptote? We know from the picture that it's likely going to be a hole, but let's prove it mathematically. When we have an equation like this, I can take a look at the top and I can factor it. What do you notice about the top? Difference of squares. So I have x minus 1, x plus 1 over x minus 1. Oopsie. X minus 1. When we're dealing with equations, factoring will always help you make it a little bit more simple. I can cancel out, I can cancel out the common factor x minus 1, and I can really just focus on the limit as x approaches 1 of x plus 1. And I know that this is going to be 2. That's much easier to see. However, when a factor is crossed out, so when factor is crossed out, this means we have a POD, point of discontinuity, or in other words, we have a hole in the graph. So where x equals 1, the value of the graph looks like it should be 2, but the 2 represents a hole in the graph. If we had a situation, and I might come up a little bit later, but I'm just going to do the example now that we're talking about it. If I had something like x plus 2 over x plus 1, I cannot simplify this at all. So because I can't cancel out the bottom tells me that I have a vertical asymptote where x equals -1. So if you have a factor in the denominator that cannot be crossed out, then this represents a vertical asymptote. If you have a factor that can be crossed out, then you have a hole. All right, let's take a look at a trig example, everyone's favorite. So when we're looking for the limit, we never need to worry about what is actually happening when x equals the number we want. We're only looking at trends. So here is example 3. Find the limit as x approaches 0 of sine x over x. I can't simplify this, so I know I don't have a hole. I have something else going on here. Let's do our chart. X here. Sine x over x here.
Can we just call it f of x?
Sure,
Okay.
you absolutely can just call it f of x. Save yourself some ink, absolutely. So left-hand side, let's say, because this is 0, let's say we're going from -0.1, -0.01, -0.001. From the right, I'm going to actually write this one backwards. +0.1, +0.01, +0.001, and I'm looking for these two to be approaching the same number. So back to my graph. Clear. I'm going to type in my new function. I'm going to go to my table of values and type in what I got. Make sure you're being careful with your negative and positive values there. Okay, you can see it is approaching the value of 1. So this is 0.99999 forever almost. This is 0.9998 something. And same with the negatives, right? Sine the graph is symmetric, yes. So your answers will be symmetric too. 0.999 dot 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 dot. So both of these are approaching the value of 1. Yes, sir.
You know, you said 0.99999. Mine just says 1.
Ah.
How are you supposed to figure that out on test?
By the end of this chapter, you'll know. That's a great question, though. The reason that your calculator is showing you a 1 is because there's so many 9s, it's just rounding it because the number of 9s doesn't fit in that window. You will know the difference very soon because we're looking at a trend. And you also know that x can't actually be 0, so otherwise we'd have an undefined denominator. Okay, so we have a limit that exists. I'm not going to rewrite it. I'm just going to add it up here. The limit as x approaches 0 of the function sine x over x equals 1. All right. As with every new category of math, we have a set of laws that we follow in order to make our life easy. if you look at them, I'm hoping you will naturally know all of them by heart by the end of today, because they make very logical sense. If you take the limit of a sum of functions, it is the same thing as taking the limit of each of the functions and summing them afterwards. Does that make logical sense? Right. So if you do it by pieces or all together, you're going to end up with the same answer. Same as taking the difference. You can take the difference of everything together and then do the limit, or take the limit individually and then take the difference. This one, students tell me they understand and then they mess up on a test. A constant that is multiplying your function has no effect in terms of the limit. So if you have a C value, a constant that is multiplying your function, just put it on the outside. Deal with the simplified function first, and then deal with multiplying the constant. Okay? So simplify as much as possible. Product rule, same thing. If you see a more complicated function that looks like two things being multiplied, take the limit of the two things separately and then multiply them together. Same with division. The only added restriction, of course, is that your g of x function, your denominator function, can't be 0. So these look very, very similar to some other rules that you already know. Yes, sir.
For the number 5.
Yes.
Could so like can we go back to example 2 and how it's like it has an x in the numerator and x in the denominator, so we can apply that to that rule?
Say that again. If I go back to example 2.
Yeah, so since it has a function, since it's like one function is dividing another function, so we could use the division law.
Yeah, you could absolutely use the division law. You could call the numerator f of x and you could call the denominator g of x. Take the limits separately and then do the quotient. Yes, absolutely. Okay, this one here, exponent rule, very much the same. If, there's a big if here. If n is a positive integer, then you can find the limit first and then apply the exponent, or vice versa, apply the exponent and then take the limit. And it also applies to the roots. Okay, so even though I'm going to tell you memorize this, I'm hoping that like, oh yeah, that makes sense. You can already kind of sort it out. So here's an example 4. Take the limit of this function. This is a polynomial. You could write the entire polynomial into your calculator and do a table of values, or let us just split it up. Because I don't have a denominator in here, I could just look at what is the limit as x approaches 5 of x squared. Look at it and say it out loud. $25. Yeah. This is going to be 25. What is the limit as x approaches 5 of 2x? 10. What is the limit as x approaches 5 of 3? Just 3. So 25 plus 10 minus 3 equals 32. Done. Yes, sir.
Could you factor out the x squared plus 2x minus 3 and do that?
Sure. You could do x of x plus 2 minus 3. Oh, yes, you can. You can do it this way. You can do it x, what is it, plus 3x minus 1. Sure, you can do it that way. You can do it any way you want. as long as mathematically the result of your splitting up the function is still the same as the original function, split it up however you want. Yeah. Okay. Same thing with example 5. I can do many ways of doing this. The easiest way, of course, is to say numerator is f of x and denominator is g of x. Even simpler is to say, hey, I'm going to do f of x plus g of x plus h of x all over j of x plus, what's the next letter? K of x. You can look at it individually. You can look at it as top and bottom. You can look at it in any kind of way that you want, as long as the broken up function comes together and is still equivalent to your original function. You can use any of the laws to make your life easy, because we want to work smarter, not harder. Yeah? Okay, so if I did it this way, as x approaches 1, what is my first limit? 1 minus 5 plus 1 over 1 plus 2, which gives me
5 over 3. Negative 5 over. No, wait. Negative 3 over 3.
yes.
Negative 3 is negative 1.
Correct. Beautiful. You see how much quicker that is? Yes. So whenever you see something ugly, try to factor or try to break it up. Use the limit rules to your advantage so that we're not wasting time fiddling around with our calculators. Yes, sir.
Why do we start with that?
Because I need you to understand theory before you understand shortcuts. Teaching you shortcuts before theory means you're going to make mistakes, because sometimes if you don't understand the theory behind something, this is where people do silly things like this. The math teacher's most hated thing: x squared plus 3 over x minus 2. This is x plus 3 over negative 2. No, it frickin' isn't. Don't do that, right? But if you teach someone the shortcut method of factoring and, like, you know, you can reduce powers and they don't understand the theory behind factoring, they do dumb things like this. Don't do this. Okay. Direct substitution. This is also going to make your life way, way easier. If f is a polynomial or a rational function. Okay, what is these definitions? What is a polynomial? Yes, an expression f of x that has multiple terms, ax to the power something plus bx to the power something, ... So this is a polynomial. What is the definition of a rational function?
1 over x.
That is the base of a rational function, yes? Yeah. A poly over a poly where the denominator is not 0. Okay, so if you have a polynomial or a rational function and a is in the domain of f, means in the domain of whatever you're looking at, then you could substitute directly, just like we did in the last page.
So if a is not a point of discontinuity, or like
correct, yes.
So if the value of a is defined,
if it is defined in the domain, then you can use direct substitution. So let's go back to my previous example here. 1 is in the domain because it does not violate the restriction that x can't be negative 2. So that means I can just throw 1 into the function and decide what the limit is. However, excuse me, in our previous example here, 0 is not in the domain of this function. Therefore, I cannot substitute it directly. Does that make sense? So if it doesn't violate a restriction, you can just chuck it right in and evaluate as is. So let's take a look here. As x approaches 3, what is the restriction in my domain? Has to be, so x squared plus x has to be greater than or equal to 0. So that means x plus 1 has to be greater than or equal to 0. That means x cannot be 0 and x cannot be -1. Everything else is fair game.
But you can't take the root of 0. You can't
Oh,
take
sorry. Yes. Thank
it.
you.
That's why.
Equal to or greater than. Thank you. Thank you. Thank you. Okay. That would make it 0. So, okay, let's see this. X can be 0 and -1. So therefore my domain, apologies here, I misspoke, must be greater than or equal to -1. Does that make sense? Okay, so did I say something wrong?
Hold on.
Anything works.
Okay, let's do it the proper way. Ms. Gordon's going to stop factoring for no reason. Must be greater than or equal to 0. So x squared must be greater than or equal to -x, which means x has to be greater than or equal to -1.
Imagine, like, say you use negative.
Yeah, that makes sense.
Would any number work?
Say you use -2 and you square -2, that's 4.
Mm-hmm.
-2, that's still 2.
Miss Gordon, we're square rooting the negative x on the other side.
Wait. No,
I
what we're doing
minus-
is we're multiplying, right? We're multiplying x by x. No, here's what we're doing. We're multiplying x by x. So we just divide x by what? Oh, I understand. Never mind. You're right. Okay, so x squared just becomes x times x, right? So you move one of those x's and divide it on the other side.
Hold on. Why would I divide?
Pardon? Why would you divide? Because the opposite of multiplication is division. Yeah, and then x is, and then you cancel out the x's on that side. That becomes -1, and then x on this side becomes x.
Are you saying that I did it wrong or that I did it right? I
I'm
don't.
on your side.
Oh, you're on my side. Okay, got it.
But like anything works.
It does. No.
Does it work? Okay, well, let's. Okay, Kate. Let's test our theory. If I say -3, -3 squared minus 3 is greater than or equal to -1.
It should be greater than 0.
0, sorry.
That's 6, yeah.
That is 6. Okay, then cool. We don't have restrictions.
So why did we do all
I keep missing my domain and range. Okay, the domain x is all reals. Therefore, 3 is in the domain. So the limit, just chuck it in. Can you simplify this? I'm going to exercise your radical. How'd you get that? This is like 4 times 3 simplified. Okay, can I give you, take 2 seconds. Can you simplify the following? Take a moment. What does this break down into? Yes, how did you get that?
9 times 6 is.
Because this is 9 times 6. Okay, what about here?
Oh, that's- You have to use your logic.
It's not prime.
It has a 4 at the end.
Okay, if I prime factorize, I get 19, 7, 2, and 4. So what is my,
2 root 19 times 7 times 2.
I stop here because I don't have any roots below, right? Okay, next one. 2 root 521. We happy with that? Cool. Do you remember doing this?
Yes.
It's going to come up. Okay. I want to make sure we're ready to do that. Okay. I think we're at the very, very bottom here, our last little bit of our lesson. Functions that, functions with direct substitution properties are called continuous at A. Continuous means they exist at the point A. So whatever my point is at A, the limit exists. As long as I can use direct substitution, it is continuous. Means the function continues right through that point. From the left, continues right to the right.
Well, up till this point, we've been using functions that aren't continuous.
Some have been and some have not been. We've had a mix.
Okay.
But if you have a polynomial or a rational where A is in the domain, we call this continuous at point A. So for example, for the limit here, one of our examples, I think it was example 1 or 2, where we had this as our function, we can see, we cannot use direct substitution because we have a denominator that has an x cannot be 1, so we can't just plug it in. However, we could, as we did before, factor, simplify, and now we have created or simplified this equation into a property or a function that we can use a distributive property in. So I could just put the 1 in here and say, okay, it approaches 2. However, my comment will be that it is discontinuous. Now, because of the things we factored at x equals 1, but the limit as x equals 1 of the function equals 2. So the limit exists but is discontinuous. Sometimes you will get lucky and get functions that do factor out, that you can use direct substitution, and sometimes you won't. Just depends. Okay, in general, if we have a function f that equals the function g when if f and g are equal when x is not a, then the limit of f and the limit of g will also be equivalent. Meaning, if we have a rational function and we call the top f and the bottom g, we make x not equal to a, but it approaches a. If the functions are equivalent, their limits will also be equivalent. Okay, next example. You could use the limit rules and split this up into 3. 1, 2, 3. However, I want you to try expanding the numerator. Is there a way that we can just reduce this down to a polynomial rather than a rational? So if I expand the top, limit as h approaches 0, what am I going to get in the top? Okay, but
Oh, it'll just be like H in the bracket. Oh, you want everything?
I want to do the entire thing, h squared minus 9. Okay, so then I see the 9s are canceling out. You guys did lots of steps in your head, which is good. Means you're comfortable with this. So this is h bracket 6 plus h all over h. All right. Now I can use direct substitution. Right now, this simplifies to the limit as h approaches 0 of just 6 plus h. So I put 0 in here. This tells me that the limit exists and it is the value of 6. Okay, so sometimes factoring helps and sometimes expansion helps. Play around with it. Yes, you had a question. This would be discontinuous at 0. Yes, because we have a denominator, we have a point of discontinuity. So the limit exists, but it is discontinuous. Same with example 8. I can see that the bottom is just a t down there. I know it can't be 0, so it's discontinuous. But I can do some magic tricks here and figure out what can I do in order to, yes, hi. Simplify it. That was the end of my sentence. Now I can say yes. Hi.
Sorry. For like this, what the what's it called? The first one we proved that it's gonna be discontinuous, even though like we have a limit.
Yeah.
Will we, so how does like what will the question look like if there is no like limit and it's not discontinuous, like in this situation? So if we're expanding it, so like will we not get any solution at all for that if we don't have a limit?
Yeah, if you don't have a limit, you'll say D and E, or you'll get a limit that makes no sense and goes off to infinity, like we had yesterday. It could be many different things. Your job is to find it. So let's do one last example before the bell goes here. Okay, I cannot factor this. I cannot cancel any common things. I'm going to ask you to rationalize the numerator. Rationalize the numerator. I can't use substitution because my denominator is t and 0 is not in the domain, so I can't do that. So I have to find a different method. Factoring, can't do. Expanding, can't do. So my next thing, I see a radical. Where would you factor?
Wait, there's a negative 3 outside. That's sorry.
Yeah, so I can't factor. I can't expand. So I see a radical. My next thought is, let's try rationalizing. So I'm going to multiply top and bottom, t squared plus 9 plus 3. T squared plus 9 plus 3. Okay, the top, I have a difference of squares. So this is going to be t squared plus 9 minus 3 times 3 is 9 all over t squared, and I'm just going to leave the bottom in brackets. T squared plus 9 plus 3.
You can factor out the t squared.
Yes, 9 and 9 go away. I have a t squared on the top. I have a t squared on the bottom. Now I can factor them away. What is in my numerator? Thank you for not saying 0. So the limit as t approaches 0. I have a 1 in my numerator. I have t squared plus 9 plus 3. Now looking at my new simplified function, is 0 in the domain? Yes. So I can use direct substitution. Instead of t squared, I'm just going to throw a 0 in there. 3 plus 3, that gives me 6. 1/6 is my answer. Correct. Okay. So things we're going to try to make our life easy. Factor or expand or rationalize. Okay? If you see brackets, try expanding them. If you see a polynomial, try factoring. If you see a radical, try rationalizing. Anything to get it into simpler form. Questions, comments, concerns? Homework for the day is posted there. Tomorrow we are going to have a quiz. Can I just have your attention? 2 more minutes. Have your attention, please. Your quiz is going to be about, let me just double check here. It's going to be 2 questions. Okay, you're going to find a limit using the stuff we learned in lesson 1. And you're going to be asked to find a limit using what we learned today, because today and yesterday's lesson are kind of together. Okay, so find a limit mathematically using 2 different methods, lesson 1 and lesson 3. Questions? Good. Okay, dismissed.